All right, so in this video, I'm going to talk about continuous distributions. In particular, I'm going to talk about normal curves. This comes from Chapter 5 of the textbook PDF that I uploaded into files in Canvas. We're going to work with problems from that chapter this week, and I'm going to finish you up with normals probably the very first of next week. So normal distributions occur quite often. They come up in every statistics course and sometimes in other algebraic-based courses where you're just talking about the distribution itself and not necessarily tons of statistics. All right, so a little bit of vocabulary. Normal distribution is continuous. And let me just draw a little example down at the bottom. So normal distribution has a horizontal down here and it has a bell-shaped curve that is similar to what I've drawn right there. It goes all the way out, it just continues going all the way out to infinity. And this bottom part of the curve, or this left-hand side part of the curve, goes to negative infinity on that side. It has area underneath. The area underneath is equal to 1. And the function can never be negative. In other words, that line is never going to touch that horizontal, and it's never going to cross the horizontal. This is a normal distribution. If you talk about a standard normal distribution, and what we're talking about, we go back to z-scores, and this very center right here is 0, and you've got 1 standard deviation away, 2 standard deviations away, and 3. On this side, you've got 1, 2, and 3, and it goes out. I mean, you're going out to infinity, so I mean, you're going to eventually get to 10,000, 10 million, and so on. But what we're working with is typically the majority of the area falls between negative 3.49 and 3.49, really. So you're not going to get much larger than the small sketch that I've drawn here as far as the area. However, the area itself does continue on to infinity on both sides. It's just negligible because it's so small. The gap between here and here just becomes so small on either side, all the way out to infinity or negative infinity, that it's really negligible. 0.0000, etc. numbers as far as the area goes. So that's why the area equals 1 for the entire curve, but almost 100% of it falls within this area right here to right here. Okay? And the mean, the median, and the mode are equal. So let me just come back to a little small sketch. I do not like this color I'm using, so I'm going to go to dark green. So in a standard normal curve, the mean is 0 and the standard deviation is 1. If you remember, this is Greek letter mu here, represents population mean, and this is Greek letter sigma, represents the standard deviation. So you got the population mean with mu, and sigma represents the standard deviation. So when you're looking at the curve itself, you've got 0 right here in the middle, and that is the mean, the median, and the mode. They all fall at 0. You got 1 standard deviation, 2, and 3. And if you remember, I did the same thing on this side in the last sketch. And right here in the middle, the median is here. The mean is here. So those measures of center, to include the mode, are right there at 0, which means if it's the median, then we have 50% of our data on this side. And we have 50% of our data on this side, and that's from a previous lesson this semester. So that tells us a whole lot. That tells us that the area underneath the curve on one side is simply equal to 0.5. And I just pushed that far out so I'd have room. And then if you look at this side, the area is 50% of it, so that also is going to be 0.5. It's asymptotic, which means that it approaches the horizontal. So, this line right here approaches the horizontal but never actually touches it. And as I mentioned a second ago, it never crosses. The inflection points I'm not going into at all, but basically it's where the curve changes direction, and it's at a standard deviation of 1 away from that mean, median, mode center. Okay, this is the formula for a standard curve. If you were going to graph a normal curve using a regular function, this is what the function would look like. And I'm not going into detail with this. I use this for my college stats course. So looking at a bell curve, remember I talked about the area underneath the curve. This area underneath a normal curve equates to probability. And we use it in probability scenarios. We use it in research studies. We talk about the normal quite often. And it's very easy to work with if you change your data within the normal to a standard normal distribution. And we'll do a few problems in just a second. So if you notice right here we're at 0. That's where your mean, your median, and your mean fall. We go out 1 standard deviation there, 2 there, 3 there. I did talk about the inflection point, but not in any detail, but it's right here where the curve starts changing direction. Whoops. In either an upward or downward slope. And then on the other side, we have 1 standard deviation away. The negative indicates direction. You're just to the left of that center as you're facing it. 2 standard deviations away to the left and 3 standard deviations away to the left. All right. When we standardize a normal curve, remember I talked just verbally about this, but we have actually talked about this in another lesson. Whoops. When you have data, you use the z-score to find out what the z-score formula to find out what the z-score is. For example, let's take this 1030 right here. Now by the drawing, I'll go ahead and tell you, by the drawing, we're looking, oops, that's not a very good color. We're looking, this is 0, this is 1, this is 2, this is 3, -1, -2, -3 is what it looks like to me. But I'm going to actually figure it out. So what I want to know is, I have a normal distribution with true data. 1010 is the mean. So 1010 is the mean. The standard deviation equals, looks like 20. So that 1010 plus 20 would give me 1030, assuming that 1030 is 1 standard deviation away. It looks like it is. It is by this second picture over here. So the z-score, if you remember, is your x value. Subtract your mean divided by the standard deviation. We're looking at 1030. So I've got 1030 subtract 1010 divided by 20. 1030 minus 1010 is 20 divided by 20 equals 1. So the z-score for the data value of 1030 is 1. So we use the z-score, we standardize it, and again, the reason we standardize a normal curve is because we are going to use that standard normal. We have tables for the standard normal. We have numbers that we can pull out with the standard normal. We don't with any given curve. So we have to standardize it first before we can work with it. All right, I've got a few more slides. I'm going to go through a couple of problems I want to do in this first video. So a standard normal distribution is a normal distribution with a mean of 0, standard deviation of 1. I already talked about that in a previous sketch. If you wanted to draw the following as a normal curve and a standard normal curve underneath, then it would look like this. So I am going to work with this one right here. So I've got a normal curve with a mean of 35 and a standard deviation of 4. So as a normal curve, this is going to be not nice for me to draw, but as a normal curve, it looks like this. I want to draw another one underneath it and see how close I can get. I mirrored it pretty well. So in this top curve, this middle number where the mean, the median, and the mode fall, that's where your mean of 35 is. If you map it down to a standard normal, that's where your z-score is 0. If you go out 1 standard deviation, you are at 39. And if you map it down, in other words, this middle is here, this would be here, and that's 1 standard deviation away. And we find that by saying z equals 39 minus 35 divided by 4. 4 divided by 4 equals 1. Check. Okay? And I could do the same with the normal curve with a mean of 12 and a standard deviation of 2 as well. Let's put it into practice in some actual problems here. So now we need to use a handout. Now we need to find the area underneath the following standard normal curve. So I'm going to draw these out. So this will be the end of the video. And I'm just going to draw these particular curves out. So I'm going to start with left of negative 1.3. So we are looking at 1.3, negative 1.3, 1.7, 2, negative 2.3, negative 2.25, and 0. In this first curve, the distribution looks like this. That's a little bit better. There's a normal curve. We want to find the area underneath the following standard normal curve. So we are looking at a curve that has a 0 here. 1, 2, 3. Negative 1, negative 2, negative 3. Okay? What we are looking for is left of negative 1.3. So negative 1.3 is about here. It goes up to here. So the area to the left, I'm just going to shade underneath, is all this area underneath the curve between the x-axis and the curve itself, all the way to negative infinity. So I'm going to put a handout in Canvas for you. We're going to start working with this handout so we can find out what the area is. But just looking at this, a couple of things that I know about it right out the gate. I know that the area is less than 0.5 because 0.5 is what we have from here to negative infinity. That's 0.5. So this area underneath that curve to the left of negative 1.3 is less than 0.5. So there are some things I know about this without having a table, without doing anything other than knowing, say, the empirical rule, which we talked about earlier, and z-scores. So we want to find to the left of negative 1.3. Okay. For this next one, I'm just going to draw the sketch to the left of 1.7. So again, we've got a normal curve. And we've got the mean, the median, and the mode in the center. 1, 2, 3. And I don't really need to put the other side because I'm looking right here to the left of 1.7. 1.7 is about right there on the horizontal, right there. Whoops. What's going on? About right there. And we're going to the left of, so we're looking for the area underneath this curve all the way to negative infinity. And again, we're going to use the table to find this, but what do we know about this right off the top intuitively? Well, I know that the area to the left of 1.7 is greater than 0.5. Even if that's just a small victory, it seems really easy to work with. We know that. So we know it's greater than 0.5. It's greater than 0.84. I know that because the area between here and here is about 0.34. And so it's just a little bit bigger than that. So we can find exact answers to these from our tables, from our technology. However, for tonight's opening video with this, I'm not going to work with that. We're just doing a little sketch talking intuitively about this. The last one I want to talk about on this page is this last one down here, between negative 2.25 and 0. So find the area underneath the following standard normal curves between negative 2.25 and 0. So I go 0, 1, 2, negative 1, negative 2, negative 3. So negative 2.25 is about right there. And the 0 is right there. So I'm looking at finding the area between those two z values. And I'm going to show you how to do that using the table, and I'm going to show you how to use that, how to complete that using the calculator. All right, so there's the opening into normal curves. I'm going to assign a few problems. I'm going to assign a reading section from the textbook. I'd like you to go through and read that section. try the problems. I'm going to come back through and I will add another video tomorrow that expands on this and pushes us a little bit out of just intuitively looking at it and finding some closer to exact answers for the area under the curves. And again, the area underneath the normal distribution, this continuous distribution area underneath, equates to probability. All right. Thanks for watching.